Hello, everyone, and welcome to this third episode of our webinar series for the project SENERGY NETS. The title of the today's and last episode of this webinar series, the title will be Panda-prosumer meets SENERGY NETs, and we are going to talk about application and advantages of the use of panda-prosumer for electricity grid. So my name is Matteo Filippini, and I'm a project officer for Euro Heat and Power, which is an association promoting the sustainable district heating and cooling, and it's also leading the work package on dissemination and communication activities for this project. So today we're gonna delve into the use of prosumer, which is basically an electric grid simulation tool that allows analysis of local energy flows, storage, and distributed generation in smart grid environments. And so let me just quickly go through our agenda for today. Um, so um, we are gonna have a brief introduction to the Panda tools by Pawel Lytaev from University of Kassel. So reminding us the other tools that we already dealt with. So Panda pipes, Panda Power, and today Panda Prosumer. Then we're gonna have an introduction to Panda Prosumer by Pratikshya Mohanty from University of Kassel. Then a general intro to the SENERGY NET projects by our project coordinator Renato Luise. And then we're gonna let's see two different use cases based on the use of Panda Prosumer. One led by Marko Keber and the other one explained to us by Hyacinthe Ménard. And then the end, we are gonna have a Q&A session. So please remember that we have a Q&A box down on your screen where you can drop messages and doubts and questions that we're gonna take into account at the end of this webinar. So let me just start at this point, and we start with Pawel Lytaev from University of Kassel. Pawel, floor is yours.
Great, thank you. Yeah, hi everyone. My name is Pawel Lytaev. I'm a research associate in the University of Kassel, and yeah, today I'm here to introduce you to the set of Panda tools that we develop or use in SENERGY NETs. So let me go right into it. Yeah, so of course, I will give you an overview and go into the depths of each tool. So the Panda tools are namely Panda Power, which maybe some of you already know, Panda Pipes, which probably some of you know, and pandaprosumer, which is basically the newest tool that we put also open source, but more on that later. So just a quick overview over the webinar series. So we are here in the third part. The first two parts were already held in February and March, and they were about Panda Power, which is an electricity grid simulation tool, and Panda Pipes about pipes networks. Both are already on YouTube, so you should check them out. And yeah, today we're talking about Panda Prosumer. Quick overview what the tools can do. So as I said, Panda Power is an electricity grid simulation tool. It's already open source since 2017, so you can find them on GitHub. You can also see the link. It has already over 800,000 downloads, and it's uprising. And yeah, and about Panda Pipes, we released it in 2020. By the way, both tools are developed in close cooperation between the University of Kassel and the Fraunhofer Institute here in Kassel, Fraunhofer IEE. And Panda Pipes also already has around 66,000 downloads. So yeah, pretty good in my opinion. And now released since April is pandaprosumer, which goes into more depths on the prosumer side, but again, More on that later. Let's talk first about Panda Power. So if you see here on the right side,
That's okay, man.
different consumers and generators connected via power grid. And what does Panda Power do? It basically simulates the power grid. So you can simulate line. Then it's an easy to use open source tool for power system modeling. The core functionalities are based on PyPower, so it uses mainly Newton-Raphson algorithm for the load flow. We extended it further with more features like optimal power flow, state estimation, topological searches, so you can automate your grid search, short circuit calculations, and we are still extending, so more features are there to come. For example, also asymmetric power flow. So the list is quite long. And why is it so good to use Panda Power? Well, it's Python based, so you can connect a lot of different Python packages to it, like PyTorch, like for AI applications, PyOmo for optimization applications. You can also easily process input and output data with pandas. So it's very flexible and also very easy to automate your processes. So that's basically one of the big advantages of Panda Power. Regarding the use cases, so it's already deployed a lot. As I said, already over 800,000 downloads. We successfully deployed it to multiple TSOs and DSOs worldwide. Of course, applied it in several grid studies. So whenever you read a paper, often Panda Power is cited. Then going on to Panda Pipes. So Panda Pipes focuses on pipe grids, so mainly district heating and gas systems. It's also based on the same concept of Panda Power, based on the library of pandas, which maybe many of you know. It's also Python-based and open source, so the same advantages regarding automation of processes hold also here for Panda Pipes. The good thing is in Panda Pipes also is that you can combine it together with Panda Power and simulate multi-energy networks. So if you have a distribution grid where you have an electricity site connected to a district heat network or a gas network, you can combine them in all in one simulation in Panda Pipes. And the use cases where it's already shown its potential are basically urban water supply, district heating networks, gas distribution. And I think on the district heating network and the potentials there, I think Hyacinthe will also talk a bit about that later. Now the main topic for today is pandaprosumer. So when you see Panda Pipes and Panda Power, you can say they are focused on the grid, but the consumers, the prosumers, the generators, sector coupling elements, like here on the right-hand side on the picture, the heat pumps, the CHP plant, pandaprosumer goes into depth of modeling those and gives you the possibility to model those prosumers basically in more detail and connect them also to a grid. Common use cases where we use this are prosumers with different sector coupling, as I said, but I won't spoil too much now. The other speakers will tell you way more about that today. And it's now open source, so you can feel free to check it out on our GitHub page. The link is on some previous slides. So to conclude my part of this webinar, we have Panda Power, Panda Pipes, pandaprosumer. We combine them here in the SENERGY NETS project, let's say, as the Panda tools. So with Panda Power, you can simulate the electricity side. With Panda Pipes, the district heating and gas side, or also in combination with the electricity side. And with pandaprosumer, you can go into more detail. You can simulate very thoroughly, let's say, sector coupling elements, which you need in the distribution grids of the future. Yeah, and I would say thank you for your time and the attention, and I will then handing over to Renato. Oh no, sorry, Pratikshya. Sorry.
Okay, thank you for the introduction on all the Panda tools. And from here on, we will discuss a bit in detail about Panda prosumer, namely its structure and some theoretical basics. The agenda looks as follows. We would start with the concept of panda prosumer, bit on how it looks like for the end user and the advantages that come with it. The overall panda prosumer structure, namely the prosumer controller, which is the core of panda prosumer. Then we would dive deeper a bit into functionalities, namely which are implemented as interconnection between different controllers as mapping schemes, and also a bit more into time series and finalization. So here, what you see in this picture is a brief overview on what Panda Prosumer does. So as you know from before, Panda Power is an open source tool used for modeling power networks. And this is something which has already been put to use and been implemented for grid planning for large network operators. Similarly, Panda Pipes is also an open source modeling tool for modeling gas and heat networks, which has already been implemented also for several multimodal distribution network studies. And now Panda Prosumer sort of acts like a bridge or something that couples both Panda Power and Panda Pipes, and also simulates different energy infrastructures. So in the future, when sector coupling is important for for the entire change in our energy infrastructure, it becomes important that multi-energy grids are simulated, and Panda Prosumer exactly does the same. Now, here we would talk a bit about what Panda Prosumer is. So as previously mentioned, it is used to model different sector coupling elements, out of which some of them happen to be prosumers, which mean they are both producers as well as consumers. The tool has been developed as based on Python and uses pandas as its code library, which means that it's quite modular and flexible for the end user, and the user also has the possibility of using different Python packages with it. What we have already are existing models which can be used as reference for the end user, and these have already been validated with necessary literature as well as test functions. As previously mentioned, the framework consists of something called a prosumer object, which can be imagined as a container, and this encapsulates different components such as controllers, elements, period, and mapping, but we would get to that in subsequent slides. The core of this setup is the so-called prosumer controller, and this is something which is built on the already existing Panda Power control loop. Okay, coming to the advantages, Panda Prosumer is already open source, which means it can already be used and it's open to be customized to model more sector coupling elements by the end user. It also offers a flexible time series simulation, which means the user can decide the time period over which they want to simulate, as well as flexibly choose the time steps in this simulation. Then it also has the possibility of integrating more sector coupling elements rather than just the existing ones to simulate larger multi-energy systems. And finally, the user can customize the control logic as per their own operational needs, and also implement custom control strategies. As already mentioned, it's also possible to integrate pandaprosumer with district heating network as well as power grids. Okay. This slide shows the models which are currently available open source in our GitHub repository with the institutes which have developed these models. It also talks a bit about which models use which mapping schemes and in which fashion they can be interconnected. This is something which would be explained in detail in the subsequent slides, also with a tutorial to show the user how these elements can work together in a single system. Next, what we have is how the core structure looks like. At the heart of it is a prosumer controller. It takes three different kinds of inputs. One is static data, which can be imagined as something like efficiency or COP. And there is also input time series data, which means what it looks like is a demand profile over time steps, and certain natural constants, for example, which are optional. And what is embedded inside the controller is its own control logic. So it takes these inputs and then runs its control logic, and what it gives out is a time series output. As an example, on the right, we have a simple heat demand controller showing very specific static and time series data for this specific controller, as well as its time series outputs, for example. Okay, what we have here is the Panda Power time series and control loop functionality. On the big box on the outside, what you see is the time series loop, which means that it's a very simple time series simulation. It starts and there are certain time steps, and there is, of course, a data source, which can be demand profile. And what it does is the power flow runs, and if it converges, it finalizes itself and checks if there are any further time steps left. If yes, then it goes to the next time step, and and if not, it ends here. It's important to mention that the time series and control loop functionalities in Panda Power are very tightly coupled, which means that the control loop can be embedded inside the time series loop. And what happens inside this control loop is that there is a general controller, which can be something which is called as a constant profile controller. What it does is it takes the time steps and the data source and generates a time series output. If it achieves convergence, it finalizes its control and goes to the next time step. And in Panda Prosumer, what we do is that we link this constant profile controller with other controllers in a way that they are communicating. And if all of these controllers connected together converge, then it finalizes itself and goes to the next time step. Okay. Now it's very important here to understand that the controllers are connected to each other. And in order to explain this, I have a very simple example of how cellular communication works. What we have in Panda Prosumer is that there is an initiator component and there is a responder. Initiator is the one which tries to make make the communication to the responder, and also vice versa. So in this in this example, it can be understood as following. Here the initiator resembles something like a cellular tower, and responders are the cell phones which have a SIM card. The SIM card tries to authenticate itself to the network by sending certain signals. And once the responder or the mobile phone has authenticated itself, the initiator or the cellular network allots the responder a certain bandwidth or frequency to make this communication possible. And this is known as network resource allocation. So this is how it basically happens. And once the user has authenticated itself to the network registers this user, and it's open for bidirectional communication. In our case, we have mapping, which is the terminology that we use for controllers to communicate with each other. For a very simple example, what we have is a chiller and a demand. So on the left, what you see is an Excel file. For example, it can be a demand profile over different time steps. This is fed into the constant profile controller, and the constant profile controller basically generates a time series for this and provides this to the chiller controller and the demand. Once the chiller is aware of the cooling demand that it has to provide, it executes its own controller logic, and then it provides the cooling demand to the demand controller or the demand side basically. Once the demand has received the cooling power, it takes this and compares it with the demand which is supposed to be met, and the difference which is left is basically the unmet demand if there is any. We have two mapping schemes currently developed to connect our controllers. One is generic mapping, which is based on energy flows, meaning energy is used as the medium of exchange of information between the controllers. And the second mapping scheme is fluid mix, meaning fluid properties are the parameters that are used between controllers to exchange information. It's also important to mention that and the first time like in this setup, it's always the constant profile controller which executes first, and it's followed by other downstream controllers. Also important to say is that the initiator controller has to merge, which has to converge, which means that it needs to achieve convergence or execute its control step properly for it to map its outputs to the subsequent downstream controllers. Then we have a simple illustration of the generic mapping scheme. What we have here is an agent-based control, which means each controller's individual control action is independent of the following controllers or the preceding controllers. What happens is each controller takes the input time series, executes its own control logic, gives out an output time series, and certain parameters of this output time series are selectively applied or sent forward to the following controller. And if these parameters are energy flows, which are forwarded to the next controller, it's a generic mapping. It's one-to-one mapping, which means only one initiator can talk to one responder. Next, what we have is fluid mix mapping. Fluid mix mapping, as previously mentioned, uses fluid properties to communicate with the following controller. It's based on some fluid dynamic concepts as well as thermodynamic concepts, but this is something which would be explained better with a tutorial which would probably which would follow next. So I would not go much into detail here. Then what is important to mention is that in pandaprosumer we have two concepts known as level and order, and this becomes particularly important in a configuration in which there is a chiller or a heat pump, for example, and it has to meet two demands. It can be understood as following. So, for example, on the left, you see that there is a chiller and it has to meet two demands. And for the chiller, it's important that it knows that in which time step it meets which demand. And in such a situation, it is important that the mapping, as in the interconnection, is being allotted an order. And the lower order mapping is would mean that the demand that it is connected to is always met first. But this logic is but this logic can be understood right now as following. Each controller has its own order, meaning that the controller with the lower order executes itself first, and once it has converged, it forwards its output time series to the following controller. Okay. Then what you see on the right is as an illustration of what orders and level look like in a cascade control fashion when a string of controllers are connected to each other. In a single level, it is important that the controller at the lower order always converges first before it goes to the next order. It's also important to know that in a single level, all the controllers are working towards a single goal, meaning if one controller is allotted the task of increasing the voltage, the other controller in the same level cannot work in the opposite fashion, like decreasing the voltage. So all the controllers in the same level have to work for a single goal. And once that is achieved, only then it can go to the next level. And orders and levels are basically used to set up a hierarchical structure of implementing a control strategy in a system. So here I have just provided the difference between controller order and mapping order. And finally, we have the functionality of time series, which also follows from Panda Power. So we initialize the necessary controllers and data sources before the time series loop starts. And after the power flow has converged, we finalize everything and ensure that all the results are handled properly and are transferred to the next controller after the simulation period ends. Yeah, so that's all from my side about the theoretical basics and how pandaprosumer looks like, and the following speakers would present a tutorial to better explain how these controllers are connected. Thank you.
Thank you, Pratikshya, for your clear explanation. And now we leave the floor to Renato Luise, which is our project coordinator, to give us a bit of an overview of SENERGY NETS projects. So, Renato, floor is yours.
Yeah, thank you, Matteo, and thanks to everyone for participating to this webinar. Indeed, after having get a first introduction to the pandaprosumer, before getting to the real case application with the Hyacinthe, I wanted just to show you a bit what is about the project and how then we will try to achieve our goals also through the application of pandaprosumer. The project of SENERGY NETS is basically has the goal, the target to develop model for optimizing the planning of the district heating and cooling. And in the end, through, as I said, multi-energy system models to enhance the flexibility and facilitate the sector coupling for the DSO and TSO, so the distribution and transmission system operators. The project has started in September 2022, so it has now We are working on it since 2.5 years, and it has a total length of 4 years for a total budget of 10 million euros. The project consists in 9 work packages, 41 deliverables, and 12 milestones. You can see a bit how the work packages have been divided, but the most important thing that I would like to emphasize is also how the consortium has been built. Indeed, we are 19 partners from 8 different countries, and very important, we have 3 demo sites where we will go to install our model and try to optimize the multi-energy systems, and 2 additional case studies. As you can see here, the variety of the consortium allows us to have a look, let's say, have a deep insight from different point of view. Indeed, we have both research and academia as well as energy supply and services. At the same time, we have also 2 DSO in our consortium and a TSO also in the advisory board. And on top of it, we also have software providers and association and networks. As I said before, we have 3 demo sites that you can see here. They are respectively in Italy, in the city of Milan, in Slovenia, in the city of Ljubljana, and in France, in the city of Paris. The first 2 that I mentioned, so Milan and Slovenia, are mainly focusing on the city headquarter applications, while the third one in French is more focusing on a commercial center, which is named Îlot Montparnasse. Additionally to that, you can see here we have also Spain and Sweden. In this case study of Spain, we have the city of Cordoba, which is involved, and in Sweden, the city of Västerås. Additional to that, I wanted just to give you a general overview on all the several models. Of course, as you can imagine, the demo sites are different from each other, but that's what we are aiming to develop, or partially we already developed in terms of modeling. And finally, that will allow us to optimize the energy system and to achieve our goal. And with this slide, I finished my short introduction, and I would invite you, if you are not already following us, to follow on our channels, like Matteo also already advertised, on LinkedIn, Twitter, or you can just Google us. We have an official website dedicated to SENERGY NETS, where you can follow all the latest news concerning the project. So
thank you so much,
again.
Renato.
Yeah.
Thank you so much. Now I will leave the floor to Marko and then consequently to Hyacinthe, that both of them will guide us through 2 specific demo sites from SENERGY NETS. So Marko, please, floor is yours.
Thank you very much, Matteo. I hope everybody can hear me. Hello also from my side. My name is Marko Keber from the University of Ljubljana in Slovenia. I work as a researcher and was involved in this project, also in the development of some of the elements included in pandaprosumer. And I would like to take you now on a short journey of how we started using pandaprosumer and what we have managed to do with it, how we managed to use the tutorials in particular to develop a use case that we are currently working on. Okay, next, please. I hope. Yes. So pandaprosumer has an advantage that it can model both conventional systems and systems with flexible components. This is very useful when you want to compare, for example, existing systems to something new, something that you would like to develop. And in this case, we are focusing mainly on the inputs, so on the energy sources. The internal combustion engine-based combined heat and power, and the second source will be the booster heat pump. Let's see if it works. Yes. So if I start with the ICE CHP, so the combined heat and power system, it gives out two outputs. It gives out electrical power. It gives out heat. Heat as a sort of, it could be considered as waste, or it could be also recovered as useful energy through heat exchangers. And in the way it's set up in pandaprosumer, the user can choose between two outputs, which one is the preferable one. This CHP is based on an actual system, so an actual engine that's been developed by Mitsubishi in this case. It runs on natural gas, so pandaprosumer uses data for natural gas, but in different forms. So you have natural gas and then synthetic natural gases. 6 synthetic natural gases are included for information, and the user can choose between 3 sizes. Smaller one, 350 up to 1400 kilowatt of electrical output. Now, one special feature of pandaprosumer is the possibility to evaluate emissions. So there are 3 types of emissions: CO2 equivalent, a standard way of evaluating CO2 emissions. There's also the possibility to evaluate CO2 at the location, so where the CHP is installed, and also the NOx emissions at the location. So this gives the pandaprosumer the possibility to evaluate the amount of emissions that will be emitted during the operation of the CHP, not necessarily the whole system, but in this case, just the CHP. So how does it work? It's modeled as a conventional heat source. This means that if you look at the picture on the left-hand side at the bottom, the energy from the fuel comes in, and then we have the electrical power coming out and the thermal power coming out as well. There are different inputs. Of course, the static inputs that Pratikshya mentioned before that set up the size and the configuration of the CHP, and then the time series inputs or the time dependent inputs that include the temperature, which allows pandaprosumer to adjust the air density and to take into account also the altitude, the temperature changes, and how this affects the power, and can then give out several different outputs, some of which we will use to connect to other components, as I will show before. You can see on the right-hand side that you can get the mass of the pollutants, as mentioned before, and obviously the energy flows, such as thermal, electrical, and also radiation, which can be useful for the installation or for planning or designing the installation of the CHP. Now, I should mention here that the response is instantaneous. This means that it's useful for analyzing or evaluating energy systems as a whole, but it doesn't have at this stage doesn't have a dynamic response. So for very short time periods, it will not be very useful. By very short time periods, I mean seconds, but it's useful for time periods in terms of minutes, hours, and so on. Now, one advantage of this system is that we as users can use maps. It's the whole code is based on a map, which gives engine responses and fuel properties. So both of these properties are defined in separate files, which I'll show later what they look like. But the concept is this: when the ICE CHP algorithm receives the demand from another element, from another pandaprosumer component, or from an external input file, it looks at what load it will need to run to satisfy this demand, and then looks for the appropriate value, whether this is a heat flow that you want to get out, whether it's electrical power that you want to get out, radiation, and so on. So it will look into a sort of a table, look at the load and look at the associated values and give this as the result, or use it as an input for the calculations. This, as I mentioned, it gives pandaprosumer great flexibility, because the user can, as you can see here, the user can add maps, modify maps, change them in any way they like. The maps are based on standard CHP specifications. So if the data is available, the user can use this data. If the data is not available, the user can use zeros, and the program will work just fine. This is not hard-coded, which means that the maps are, as I mentioned, in a separate JSON file. You can find in the pandaprosumer folders, in the library folder specifically, and there you can change this as you wish. Now, how do we start with building these models? This is an example for the IC-CHP element. So first, we define obviously the properties of each particular element. In this case, we have the size, the fuel type, and the altitude, and we can also give it a name. As Pratikshya mentioned in the previous presentation, we then create a container, so an empty container, which we fill with the data that define the element, or the CHP in this case. Okay, the booster heat pump, this is the second source, the energy source that we looked at in more detail, is slightly different. So it requires heat and power inputs, electrical power, to give out I would say boosted or increased heat. So the idea here is that there's energy coming in. The booster heat pump will provide a boost, so will increase the temperature. In the case of the heat pump, it will increase the temperature to a desired value, and this will be the output. Now, there are two types included in pandaprosumer, so water and air water, and there are three modes. So the booster heat pump needs to understand what the source temperature is, and this source temperature can come from different sources. It can be external air temperature. It can also be the temperature of the recovered energy or recovered heat from the CHP, for example, if the heat pump and the CHP are linked. There are different modes that the booster heat pump can operate in. Mode 1 will take electricity and heat. It will be limited by how much heat it gets, for example, from another element, from a CHP, how much electricity it can get from another element, such as a CHP. Mode 2 will only use the electrical energy that is provided. So if there's limited electrical energy, it will have obviously a limited output, but the source temperature or the thermal energy will come from the environment where it is installed. And finally, mode 3 is connected to the grid, and it can take, to an ideal grid, I should say, where it takes as much energy as it needs to always satisfy the demand. This is probably something that will be of use for people, for users who will design district heating or other district systems. Again, the way to create an element, to create the booster heat pump in pandaprosumer, is exactly the same as in the previous case, where we define the properties. In this case, we have the BHP, so the booster heat pump type. We create an empty element, and then we fill it with the properties. Now, we started with the tutorials to understand how how Panda prosumer works, how the elements are connected, and then we use these blocks that we understood to create our own use case, our own example, which I will show in the end. These are the four available tutorials that you will find that use the internal combustion engine CHP and the booster heat pump as the source. Now, when we're building a Panda prosumer case or an example, Pratikshya mentioned that the constant profile controller is I would say, the main element which in a way controls everything. So it reads the data that, from an external file as an input time series, and then distributes this information to all the other elements that needed. I'm showing here an example of the CHP connected to a simple heat storage and finally heat demand. So it is important to understand that the constant profile controller has a slightly different structure in how it's defined. It is a separate element which basically defines what are the inputs from an external file and what are then the outputs that go out, and these are then added to the element in a similar fashion as was done before for the CHP and the BHP. The other element that's important here, before we move on to the actual elements of the network or of the system, is the heat demand. So heat demand can be, in theory, it can be anything. It can be a house. It can be as you'll see later, a district heating system. It can be smaller. It can be big. But the important thing is that it exists in the model and that it has the possibility to get the energy from one of the elements, or could be also more, but in this case, one of the elements from the network. Another important element here is the connection between the different components. As you can see here, the elements are connected by a single arrow. That implies that we are using the generic map scheme, and it means that we are connecting the models using energy flows. So in our case, because we have heat demand, because we're interested in providing heat to a consumer, we use thermal power, or in this case, it's written in the ICP CHP controller logic. You can see this as PTH out. That's the thermal power that goes out of the CHP into the storage, and then from the storage you have Q demand that goes into Q received, and this is what the system provides to the final consumer. And at the same time, the final consumer also has to understand what kind of demand is expected, or what kind of demand we want to model or simulate in this case. And as mentioned before, the constant profile controller connects directly to the demand, and it tells it what kind of demand it wants to expect. The top arrow will tell it what kind of demand it gets, and then it can show the difference between whether it's satisfied or not. So what does this look like in Panda prosumer? It's relatively simple because we have a relatively simple connection. So we have, for each arrow which represents a connection, a mapping, we have a definition of the initiator column, so what goes out, and the responder column, what comes in. And you can see in this example that on the slide, all of these are energy flows, which means that we are limited only to energy in this case. In our case, that works fine. In some cases, it might not, and you will see this in further presentations how this is treated in Panda prosumer. Now, just to give you an example of what the results look like. So on the left-hand side, the demanded heat. So the input is an example of a single day in a factory or let's say in a production unit where production starts at 6 o'clock, increases to a certain relatively high level, and then drops off at 6 in the evening. What we see is that the demand is not met. I put this here intentionally just to show how the CHP responds in this case, because the CHP is not big enough. It will not be able to satisfy the demand on its own, and that's why the storage, which fills up very quickly, is depleted when the demand exceeds what the system can provide. But you can play around with these tutorials, and you will get very interesting results. Now, to move on to what we did, or what we're doing at the moment still, how we're using pandaprosumer in an actual case. We're looking at a district heating system, and we're trying to understand if there's a way how we could revitalize an old district heating system. So district heating system basically means there's a heat source, a heat distribution, a network, and then there will be usually more than one consumer. And in the case that we're looking at, this is an older system. We have one source, one energy source, one big energy source, lots of consumers, a very complicated network. Now, new technologies now make it possible to use more flexible approaches and things that maybe use prosumers instead of just producers and final consumers. Lower temperature regimes, this is what we're interested in, because lower temperature regimes automatically means lower energy losses, better economics for the district heating system. And our idea is to basically replace a bigger CHP that's that uses coal, burns lots of coal, with smaller one that uses natural gas and internal combustion engine and a booster heat pump. And this is what it looks like. So we have in this picture in the middle, you can see there's a very complex network of pipelines that make up this distribution network of the district heating system. But there are also areas that are less complex and that are basically that could basically be cut off. And the idea is to replace the bigger one, a bigger CHP plant, with a smaller CHP plant, which will give us not just the flexibility, but also reduce environmental impact and so on. And we can easily use lower temperatures immediately from the source. Our approach was to use a 700 kilowatt CHP. This is included in pandaprosumer, and a much larger BHP size, so a much larger booster heat pump than the one you will find in pandaprosumer. But because this is an open source program, you can basically go in and change the values, or change the logic of how a particular element works in pandaprosumer. This is just an example to show you, but when you start working with it, you will see that it is possible to do it quite quickly. And to give you an idea of the results that we got, now please keep in mind that these are preliminary results. Obviously, we are still working on it and then trying to optimize the system. But you can get basically the idea of what it looks like. So this is in mode 3, where we get electricity from outside, and we get the temperature from the CHP, and the booster heat pump tries to satisfy the entire demand. And if you look at the top two graphs, you can see that the booster heat pumps follows very nicely what the demand is from the external file that we give it. So the next steps are obviously optimizing this system. One thing that we would like to do is understand if you could combine these two elements, these two sources in parallel. This is in theory possible. We have tried it. We have had some issues because we are using the generic mapping scheme, which means that we need to understand how to divide the energy flow between the two sources. This is still something that we're working on. And we're also looking at the heat storage. So what can we do with heat storage? Heat storage is an element that introduces a time delay, whereas the CHP and the BHP, so the booster heat pump, are considered to have an instantaneous response. And the time delay will obviously introduce or will bring some sort of complication to the whole analysis. But we're not worried about that because we believe that by introducing also prosumers as heat sources and the heat storage, we can actually optimize this system in a much better way. Finally, the idea is then to connect the pandaprosumer components, so this source that is now made out of different elements, with the actual distribution network. And as other presenters have mentioned before me, panda pipes would be the ideal way of doing this. So we're hoping to be able to include panda pipes and panda prosumers, combine them, and get a full system analysis out of this. Now, obviously, this hasn't been this has been a joint effort. So I'd just like to acknowledge the people and the institutions who have been involved in the development, both of the elements and the tutorials, and finally of the case study. And I would like to thank them here for their contributions. And I'd like to thank everyone for your attention. And if you have any questions, please do reach out by email, and we'll get back to you. Thank you.
Thank you, Marko, for all your explanation. And now, Hyacinthe, floor is yours for the second demo site.
Thank you, Matteo. So yeah, I will present you the use case of Paris. So how we are starting to model the demo site of Paris that is part of the SENERGY NETS project. So I'm Hyacinthe Ménard from EIFER in Germany, and I'm working on the pandaprosumer library and the modeling of the different demo sites of the project. Yes, so I will start by presenting an overview of this demo site of Paris, and then how I use pandaprosumer to create a simple model of the system, then how I use the coupling with panda power and panda pipes, and finally the next step and challenges that I face that we're still working on in SENERGY NETS. So the Paris demo site is located in the Îlot Gaîté Montparnasse, which is a set of different buildings in Paris that include different systems, energy systems that can either produce or consume it. So you can see we got on the top some food halls and commercial centers, and on the bottom right some offices. So this system can either produce or consume some heat and can exchange this heat with an ambient temperature loop. So this loop is operated by Dalkia, which is part of EDF and one of the partners of SENERGY NETS. This loop is also connected to a storage to storing the water, as well as the white cooler that will be used in the case where the temperature in the loop is getting too high in order to reject the excess of heat. It's also connected via heat exchangers to what is called here the CPCU, which is the main district heating network of the city of Paris. So it will be used in the case of the temperature going too low. It's the opposite of the dry coolers. So the temperature get too low, then we can use this connection to the district heating network of Paris to get some extra energy in the system. And we also have a demand of domestic hot water with heat pumps in order to reach the temperature that is needed for the domestic hot water. So I will create a very simplified model of the system within pandaprosumer. So I will not go in the details of all the models, pandaprosumer models that are available and that I will use here, but you can find the detail of the documentation and the sources that we use to implement them in the documentation that is available. The link is in the GitHub of pandaprosumer. So what I will use first on the left, I will define my commercial centers that will reject some heat. So we'll model this with a heat exchanger. I also display some typical temperatures that are used in the different part of the system. So typically I would use 47 degrees for the commercial rejected heat temperature. Then I'll use the fluid mix mapping scheme in order to represent here the ambient temperature loop and the mapping between the secondary side of the heat exchanger to the hot side, the primary side of another heat exchanger. That would make the link with my heat demand. And then the heat demand, which is a demand for heating the offices, is representing with another time series and is connected to the heat exchanger via a heat pump that allow to reach the demand temperature. Here I use some time series profiles that are actually not the real one from the side. I made them up for the example, so they're not really realistic probably. I use the fluid mix mapping scheme in order to be able to create some parallel configuration that you will see in the next steps. Because with the fluid mix mapping, I can map from one controller to another, not only a scalar value that will represent the power, but actually more in detail, the mass flow and the temperature of the fluid, and be able to calculate the resulting mass flow and temperature when two fluids will mix with the resulting temperature between being the average multiplied by the mass flows of the different fluids. So the next step, because you can see, here that my two profiles of the heat production and the heat consumption does not match. So there are some times at the beginning of my time series, the heat production is higher than the consumption. At the end is the opposite. And so in order to be able to match the demand from the consumption, we will need to include a heat storage, which is another of the model available in pandaprosumer. So that I will include in the low temperature area of the system. And then I will include the connection to the distributed network of Paris. So for this, I will use another heat exchanger and consider that the supply temperature of this distributed network is 80 degrees. And I create a new mapping from this heat exchanger to the ones that go to the demand. So now you can see that I create actually a parallel configuration when we have two different heat sources that can supply the demand. So both the commercial center and the district network can supply the demand. So we need to define a merit order because we want to define that in priority, we want to use the heat from the commercial center and the storage. And if there's no heat available from the storage or the commercial center, then we want to use in last case the connection to the DHN of Paris. And so for this, I will use from Panda Power actually the controller orders. So the controller orders I use to define in which order the different controller will execute. And what is important is, I think Pratikshya already mentioned it, that when you have a mapping between controller, the initiator should always be executed before the responder, but also we'll use the order to define the merit order of the different system by setting a lower order for the commercial center and the straight phase storage, and a higher order of 2 for the heat exchanger of the connection to the distributed network, to the external network. And then 3, 4, and 5 for the last one that go to the demand. And then I will include the dry coolers. So the dry coolers I use in the case where there is some extra heat that we cannot supply to the demand or to the storage. So if the demand is already met and the storage is already full, only in this case we want to use the dry coolers. In this case, the heat will be lost in the atmosphere and consuming some electrical power too. So we want to do this only in the last case if we cannot store anymore the energy in the storage. And so here create another kind of parallel configuration where we actually one source, which is a commercial center, and the heat produced can go to two different heat sinks, which are the storage and the office demand through the storage or the dry coolers. And so I need also to define a merit order. And for this, I will use the mappings orders that we define in pandaprosumer. So I use a mapping order of 0 that go to the storage and a higher mapping order of 1 that go to the dry cooler to define that this one has not the priority and will be used only if there is some extra heat produced by the commercial centers. And now I will show some results from this simulation on the time series. So on the left, you can see the energy that is stored in the heat storage. So if you remember at the beginning of my time series, I have a higher heat production than the consumption, which means that the heat storage will get full pretty quickly because the production is pretty high. And then at the end of the time series, it will be the opposite, and so the heat storage will get empty because it will be needed to supply to the demand. On the right, you can see the heat that is rejected by the dry cooler. And what you can notice is that the dry cooler is used only in the cases where the heat storage is full, because if the heat storage is not full, then the heat will not go to the dry cooler, but inside the storage. So it shows that the mapping order that define this merit order is working correctly. Next, I will use another feature that is a coupling to Panda Power and Panda Pipes. So if you follow the previous webinars, you may know already what are Panda Power and Panda Pipes, and it was already presented before in this webinar. So I will use what we call an energy system, that is a structure in which we can add any number of prosumers, Panda Power Grid, and Panda Pipes networks. And so I will use it to couple my prosumer energy system to a Panda Power Grid on a Panda Pipes network. So on the right, you can see in orange a Panda Power Grid that I created that is very simple with only 3 lines, 2 loads, and 1 external grid on the right. So this represents a simple distribution grid. And I will create what I call some couplings, which are some special mappings that can map an information from a prosumer into a network. In this case, these are represented by the green arrows. So the one on the top will map the power that is consumed by the fans of the dry coolers, which is one of the output of the dry cooler model, and it will map this value into the load of Panda Power. And same at the bottom, I will map the power that is consumed by the compressor of the heat pump into another load of Panda Power. And then Panda Power will make its calculation of power flow every time step after this information will be mapped from the Panda prosumer. On the left, I will create a very simple distributed network model with Panda Pipes. Of course, I will not model the whole distributed network of Paris for this use case, will not be useful. So I create a very simple one with a supply pipe, a return pipe, a circulation pump, and a heat consumer. And I create a coupling between this heat consumer and my heat exchanger in Panda prosumer. And so you can see that I already represented 2 different couplings because I need first to map the supply temperature of the network to my heat exchanger. And after I can map the result of the heat exchanger, so which has the mass flow and the Q, the power that is already actually consumed back into the Panda pipes network. And I will again show different results from this. So here on the left, you can see the distribution grid power. So this is the power at the external grid connection of the distribution line in Panda Power. So basically, this corresponds to the sum of the power consumed by the heat pump plus the power consumed by the dry coolers plus the power losses in the lines, because this is actually calculated by Panda Power already, depending on the characteristics of the lines, etc., that I put in Panda Power in the model. And on the right, you can see the heat that is supplied by the Paris district heating network. What you can notice is that it will supply some power only at the end of my time series, because this is the time where the heat storage is empty. And so when the storage is empty, we need to use this connection to the Paris DHN in order to meet the demand. So it shows that my merit order is working correctly as well. Finally, I will finish by presenting what are the next steps and the challenges that we meet in the project. So what I would like to do now is to use Panda pipes in order to model the ambient temperature loop itself, which will be way more realistic to have something that is closer to the real system. So you can see that I'm trying to make a Panda pipes model that is a bit way more complex than the one I have for now. Where every system, so the storage, the commercial center, the office, the domestic hot water, the dry coolers, and the connection to the CPCU are all different prosumer systems that are connected to the same Panda pipes network. And so this is still a challenge for now in order to be able to connect so many different complex systems to one network. But we are working on it. Then we also need to manage the cooling demand and the reversible heat pumps, because as I showed, each of these systems that are connected to the loop can both extract heat from the loop in order to consume it or reject it into the loop. So it's actually it is possible to already to use Panda prosumer to do this, but in indirect ways, and we are working on making some changes, so it's more direct and easy, because the heat pump model that we have is not reversible, for example. So we need a simplified way to be able to model both cases with heating and cooling. We also got some real data from thanks to Dalkia from the real system, and we are working on validating the simulation to check that we are actually having a simulation that is close to the reality of the operation of the system. And finally, working on connecting to an operation optimization tool. So we have a work in progress in Panda prosumer to be able to have some optimization rules, but some very simple rules that you could directly in the tool implement to switch the operation of the system during the time series simulation. But for more complex optimization, you will need to connect Panda prosumer to an external tool that will manage the optimization part. And we are already working on the architecture in Panda prosumer that will allow this connection, but it's still a work in progress. That's all for me. Thank you for your attention, and I think I give back the mic to Matteo for the end.
Yeah, thank you, Hyacinthe. I don't know if any of our guests here have any questions. I see that we don't have any questions in the Q&A, so it means that everyone explained very well, since we had no doubts, and you were very good at explaining this kind of a complex subject. So I think if we don't have questions, I think we can leave it here. So I would like to thank you, everyone, and again, let me remind to follow our project on our channels, so on LinkedIn and in YouTube, where also this webinar will be uploaded on the channels of European Heat and Power. And this also closed this webinar on the use of Panda libraries for energy grids. And again, thank you for following
sorry,
us.
Matteo.
Yeah, sorry.
Is there just someone who has 2 questions in the Q&A? So
Okay.
you can see them.
Now we have them. Okay. Okay. Thank you, Hyacinthe. I didn't see it. So will you also provide a graphical interface from Tom Ludwig to show the results?
Graphical interface. We are working on one on the SENERGY NET project, but it may not be available in the open source directly in the library. So I don't know if it will be available or not, actually. I don't think there will be any. There will probably be an easier interface in the code to make the graph directly of the results. But then to display and probably we'll do something similar. We could plan to do something similar than Panda Pipes and Panda Power for plotting the system. But it's not really planned for now, actually. Don't have many much to say on this.
Yeah, thank you. From an anonymous attendee, is there any ways to integrate in the model's absorption heat pumps and not compression heat pumps?
Actually, yes, there is one because the chiller model, there is a model called chiller that is actually an absorption chiller, if I'm not mistaken. Maybe Pratikshya can correct me.
It's compression chiller, yeah. I couldn't hear your last statement properly.
I think the chiller model, I think it's is working with absorption model, if I
Yes.
remember correctly. So yeah, I think it's this one that you are referring to in the question.
And then we have one more question, which is what is the expected time frame for the integration of Panda pipes, and will it be open source?
Yes, or typically the example that I presented of the Paris use case, probably not, but yes, there will be one tutorial that explains how it can be done in a general case, yeah, for sure.
Okay.
Okay, just to add, in our GitHub, you can already find how you can contribute to the existing models. There are like instructions, you can get in touch, create a pull request if you have something that you wish to add on top of the existing models.
Thank you, Patricia. So I think that's all. If we don't have any other questions, okay. So I hope that's all. So we can close our session. Again, thank you everyone for having followed us on these 3 different episodes, and thank you for to all the speakers to have participated to this webinar series. Again, please follow us on LinkedIn and on our website, which will be updated in case we will organize any kind of other different webinars and events related to Synergy Nets. Thank you all, and have a good rest of the day. Bye bye.
Thank you, everyone.
Thank you,
Bye
everyone.
bye.
Thank you. Bye.
Thanks, bye.